All right, let's dive right into this explainer. I want you to think about something you deal with literally every single day. We are constantly battling it, right? It's the exhausting reality of trudging uphill, the way rain falls from the clouds, and the completely ordinary act of dropping something from your hand. We're all intimately familiar with the pull of the earth. But here's the wild part. For thousands of years, the true nature of this invisible force was a complete and total mystery. And it all really boils down to this seemingly simple question. Why does an apple plummet to the ground, but the massive, incredibly heavy moon just stays perfectly suspended in the sky above us? Well, this is the grand puzzle we're solving today. It's a scientific detective story spanning centuries, and we are going to walk through the exact clues that generations of brilliant minds used to finally crack the code of the cosmos.
Section 1. Looking Up. The Gravity Mystery. To understand how the universe is tied together, we actually have to rewind history. Long before mathematical equations, we just had to look up at the stars through the eyes of our ancestors and try to make sense of the patterns. Science, it's essentially a grand relay race. About 2,000 years ago, Ptolemy proposed a geocentric model, meaning he thought the Earth was sitting right at the center of the universe. But then the baton was passed. The Indian astronomer Aryabhata hinted at a heliocentric or sun-centered concept centuries later. Then, 1,000 years after that, Copernicus proposed a definitive heliocentric model. Finally, the baton was handed to heavyweights like Galileo and Tycho Brahe, a nobleman who dedicated his entire life to patiently recording planetary movements with just his naked eye.
Moving on to Section 2, Kepler's 3 planetary laws. So Tycho Brahe leaves behind this massive treasure trove of observational data, and it falls to his assistant Johannes Kepler to figure it all out. And Kepler's first massive breakthrough was the law of orbits. He realized that the old idea of perfectly circular orbits was just completely wrong. Planets don't move in perfect circles, they move in elongated ellipses, shaped around 2 focal points. And the sun? It doesn't sit in the exact center, it sits at one of those focal points. This was a radical shift in how we viewed the heavens. And because those orbits are elliptical, a planet's distance from the sun is constantly changing. This led Kepler to his second discovery, the law of areas. He found that planets sweep out equal areas in equal intervals of time. What this means in plain English is that a planet's speed is absolutely not constant. When a planet swings closer to the sun, it whips around it faster. When it travels farther out, it slows down. Today we know this is a direct consequence of the conservation of angular momentum, all driven by a central gravitational pull. Then he hits on his third law, the law of periods. If you take a planet's semi-major axis, which is basically its distance from the sun, and compare it with its time period, or how long it takes to complete an orbit, something magical happens. Kepler found that if you square the time period and divide it by the cube of the distance, you get a profound connection. When we lay out the numbers for planets like Mercury, Earth, Jupiter, and Neptune, the quotient is almost exactly the same for all of them, right around 2.98. I mean, this was undeniable mathematical proof that a universal rule governed all planetary motion. Which brings us to Section 3, Newton's universal gravity law. Okay, so the rules of the heavens were finally written down, but it took the sheer genius of Isaac Newton to connect the dots between the stars up there and our own backyards down here. Newton hypothesized a grand unification, linking 2 completely seemingly unrelated things. He compared the acceleration of an ordinary dropping apple with the centripetal acceleration holding the massive moon in its orbit. Newton realized, and this is mind-blowing, that the exact same earthly pull causing the apple to drop was reaching all the way out into space to tether the moon. He calculated the centripetal acceleration of the moon and compared it to gravity down here on Earth. And what did he find? He discovered that Earth's gravity at its surface is about 3,600 times stronger than the acceleration acting on the moon. Why is 3,600 such a magic number here? Because the moon is about 60 Earth radii away. And 60 squared? That's exactly 3,600. The force perfectly matches the square of the distance ratio between them. This eureka moment led directly to his universal law of gravitation. The equation is beautiful. It simply states that every body in the universe attracts every other body. The force of that attraction is proportional to the product of their masses, and, this is the crucial part, inversely proportional to the square of the distance between them. Move twice as far away, and the gravitational pull doesn't just halve, it becomes 4 times weaker. Section 4. Weighing the entire planet. Now, Newton's equation was elegant, but it had a glaring missing puzzle piece.
It needed a constant to make the math actually work out in the real world, the universal gravitational constant, or capital G. Without it, we couldn't calculate actual physical forces. To find it, an English scientist named Henry Cavendish built this incredibly sensitive torsion balance. Imagine a bar suspended from a superfine wire with two small lead spheres attached to the ends. Cavendish brought massive, heavy lead spheres close to the small ones just to physically measure the microscopic gravitational attraction between them in a laboratory. The gravitational pull between these spheres was so slight, but it caused that suspended wire to twist just a tiny bit. By carefully measuring how much the wire twisted, Cavendish successfully pinned down the value of G, and it is an exceptionally tiny number, 6.67 times 10 to the negative 11. Gravity is actually a remarkably weak force, which is why, you don't feel a gravitational pull from the coffee cup sitting next to you. It takes planetary amounts of matter to create a noticeable force. But because he finally found the precise value of G, Cavendish did something astonishing. Scientists already knew the radius of the Earth, and they knew the acceleration of gravity at the surface. So, with G finally unlocked, Cavendish gave humanity the final tool needed to mathematically calculate the entire mass of our planet. That's exactly why the famous historical phrase states, "Cavendish weighed the Earth." And finally, Section 5, How Gravity Changes on Earth. We've talked a lot about cosmic orbits and massive spheres. Now let's bring it right back home to your actual physical experience. You might think gravity is just a flat constant everywhere, but it really tests our intuition. Obviously, if you fly high above the surface in an airplane, gravity decreases. That makes sense based on Newton's law. You are increasing your distance from the Earth's center. But here's the twist. If you dig deep down into a mine, gravity also decreases. You'd probably assume getting closer to the center increases the pull, right? Actually, scratch that. Mathematically, as you go down, the outer shells of the Earth above your head cancel each other's gravitational forces out. You are effectively being pulled by a smaller and smaller sphere beneath your feet. Which leads us to a pretty fascinating question. If the gravitational pull gets weaker when you go up into the sky, and it also gets weaker when you dig down deep into the dirt, where is gravity at its absolute maximum? Completely counterintuitively, the maximum gravitational acceleration of Earth is exactly where you are sitting right now, right on the surface. Going up weakens it, going down weakens it. The surface is the absolute gravitational sweet spot.
So the next time you drop something on the floor, think about the sheer scale of what is happening. The very same invisible mathematical thread pulling that object down is simultaneously tying you to the stars, the planets, and the entirety of the cosmos. Every single mass is pulling on every other mass. I'll leave you with this mind-bending thought. As you sit there, the Earth is pulling you down, for sure. But technically, your mass is pulling the Earth up toward you too. What other unseen universal forces are shaping the reality around us right now? Keep asking questions and keep looking up.